if we think of DNA in terms of a ladder, we can think of the sides as rails and the part in between, the nucleobases, as steps. And the connecting molecule between the rail and the steps is deoxyribose. Now, I scanned the internet, and it turns out Wikipedia doesn't have a ball and stick model of deoxyribose associated with its entry, but I did find some models on the internet, and this one appears to be the most lucid. So let's go with this. First thing we do when we encounter a complicated molecule is try to break it down into simpler structures that we can work on, and then we can assemble the simple structures into something that's into the whole. So what do we have here? Well, first of all, we have the pentagon ring here, and then connecting to it is this structure here that looks like a water molecule, except that it has a carbon. And then we have this snake right here with hydrogen ends and an oxygen and a carbon. And this structure here appears to be a combination of these two. So basically we only have three simple structures to worry about. This pentagon, this thing here, and this thing here. So I decided that since they're two-dimensional, and we already know how to do two-dimensional stuff, I just go ahead and assemble. And so here's a prefabricated pentagonal ring. The bonds are at 72 degrees, as is the case with a pentagon. They're twisted 72 degrees with respect to their neighbor, and then I put an oxygen atom at the top. It kind of looks like a cherry on a cupcake. Okay, let's begin with this structure right here, since that's simple. And I already prefabbed it over here. So copy, paste, we'll put it over here where it's going to be. And you may wonder, well, where did you get that angle? What is that angle? And I couldn't find anything on the internet about the angles, but when I examined this picture here, I thought, well, that looks like 120 degrees, that looks like 120 degrees, 120 degrees. That seemed like a good default right here. And you see the same thing in these other pictures too. So let's go here, and since this is going to be in 3 dimensions, we have to twist this in 3 dimensions, so that's 3 parts to our orientation of this structure. Let's see, the first thing that we want to do is make it stand upright. So that's not exactly right. There we go. That orients it so that it will be sticking up like this, as you can see here. Now, second thing we need to do is we want this angle right here between the two bonds to be bisected by the plane that the pentagon ring is on. So we have to bring this down by a little bit. This is at 90 degrees, we can tell that. And then this is like 30 degrees. So we want to bring it down like 30 degrees. And when we have this compass rose here on this rotate tool, we just have to go 2 tick marks, and that would be 30 degrees, because each tick mark is 15 degrees. Now, one last rotation that we need to do, and that is between here and sticking out this way. And you may recall from the adenine video, we dealt with the trigonometry of pentagons, and we determined that this angle right here is off by 54 degrees. So if we have something pointing this way, parallel to a bond, and we want it to point this way, we have to twist it by 54 degrees. Now, we can no longer use the embedded rotate tool of the move tool when we've already twisted this off the XYZ orientation, when we've twisted the group this way. But we can use this tool. So we'll go ahead and type in 54 degrees, and it gets knocked over here, but that's okay. Now we'll bring this back, and that's everything that we need to do except connect it. So let's go ahead and connect it. We'll go into Face Style X-Ray. bring this in like so. Did that go in? I can hardly believe it, so I'm going to, yeah, that's okay now. Yes, so we've completed one. Now let's go to the next one on our task list. We'll use this. Again, I made the bonds at angles of 120 degrees with respect to each other. Let's see, we want the oxygen to be on top here, as shown in the illustration. So we will twist it this way. Yeah. Okay. Now, what do we want to do? We want to make this parallel with this before we go any further. So we have to rotate it by 72 degrees. If you can do the addition and subtraction math in your head, you don't need to do two steps, but you may as well if you feel convenient with using the rotation tool. And now I will twist this by 54 degrees so that it sticks up. I did it the wrong way, so go back here. Oh, no wonder, because this whole thing is backwards. We'll just rotate it around the other way. And now, well, that's not going to work. We have to use this external rotation tool and type in 54 degrees, and that takes care of that. Except we still have that angle bisection problem that we wanted, so we'll tilt this by that much. And now we can just go ahead and attach this. Get in real close to make this precise. We don't have flagpoles here, you'll notice, because these things are tilted, so the flagpoles could not match up. That's unfortunate. We could sure use them in a complex molecule like this. Okay. Finally we have, well, not finally, but here we go. We have this one. And in this case, you'll notice that the oxygen atom is down below, underneath the carbon. So we'll have to twist this the other way to make sure that the oxygen atom is kept below. Okay, that seems to work. Then we'll twist this around. Okay, and then twist it like so. Oh, but we still have to do that 54 degree trick. So we will twist like this, 54 degrees, and that takes care of that. And then we bring this in like so. Now, my screen capture application here only allows me to make videos up to 10 minutes. So in order to get this last point here on the pentagon, I'm going to have to go to a second video. So I'll see you over there.